Welcome back once again, my dear students. Today our topic is components of water potential. And before getting started, let's first of all recapitulate what is water potential. Water potential simply means the free energy per mole of water. How much free energy is there in 1 mole of water? That is, it is water potential. Okay, and water potential is taken as a measure of the capacity of water molecules to move. Okay, if water potential is more, the free energy of water molecules is more, and they will be more free. Now the different components of water potential, they include solute potential, then we have pressure potential, gravity potential and matter potential. And the equation for water potential is thus psi W equals psi S, psi P, psi G and psi M. Okay, this psi S represents solute potential, this represents pressure potential, this is gravity potential, and finally matrix potential. Okay, we are going to discuss each of these components one by one. First of all, solute potential. Solute potential is defined as the amount by which water potential is reduced as a consequence of the presence of solute in the solvent. Okay, you know that when you are going to dissolve the solute in solvent, it is water potential is always going to get reduced. Okay, because the solute molecules, they associate with the water molecules, as a consequence of which the free energy of water molecules gets reduced. Okay, therefore solute potential is always negative. Whenever you are going to dissolve solute, it will always tend to reduce the water potential, and it is therefore always shown by negative sign. Okay, you have to remember this. And solutes may be ionic or non-ionic. The solutes that you are going to dissolve, they may be either ionic or non-ionic, and accordingly water potential will get reduced. Okay, for example, in case of ionic substances, when you dissolve ionic substances in water, they will dissociate. Okay, and there will be more reduction in water potential, because the number of ions, the number of particles, they are going to get double. Okay, for example, अगर हम सोडियम क्लोराइड की बात करेंगे, you will dissolve sodium chloride in water, it will dissociate into sodium ion and chloride ion. Okay, and obviously water potential is going to get reduced more. Okay, and this solute potential, it is calculated by Van Hoff's equation, which is given on the other side. Psi s equals minus ICRT, where psi s represents solute potential. This C, it is a concentration. It is a concentration of the solute. I is the dissociation factor, or Van Hoff's factor, or ionization constant. Okay, and this R, it is the gas constant, real gas constant, having the value of 8.32 joule per mole per Kelvin. Okay, and T is the absolute temperature. By applying this equation, you can calculate what is the solute potential. Okay, the next is pressure potential, which is represented by psi P. It is a positive pressure which develops in a system due to osmotic entry of water into it. Okay, pressure potential is the positive pressure which a system develops when water enters into it. Say for example, this is a cell, it has got water from the surroundings. Okay, the pressure this plant cell will develop, it is pressure potential. And remember that pressure potential is always going to increase the water potential. It causes osmotic system to increase its volume and press against the wall. जब एक सेल में वाटर जाता है, ओके, तो ये इसका प्लाज्मा मेम्ब्रेन है. इट इज वॉल्यूम विल इंक्रीज, इट विल स्वेल. ओके, एंड this plasma membrane will then go and touch the wall, it will press the wall. And pressure potential is also called as hydrostatic pressure and the turgor pressure. Okay, जो एक सिस्टम, जो एक सेल प्रेशर डेवलप करती है बिकॉज ऑफ द ऑस्मोटिक एंट्री ऑफ वाटर, it is also known as hydrostatic pressure or turgor pressure. Okay, so now you know that pressure potential is a positive pressure which develops in a system when there is osmotic entry of water. Okay, so you can remember that pressure potential increases water potential. Now the third one is gravity potential, represented by psi G. Gravity causes water to move downward. We know that gravity causes anything, okay, to move downward. So is the case with water. The term psi G depends on some important factors. the height of water above the reference state of water. What is the height of water column? Okay, if you are calculating the psi g for water, first of all, the first factor that you have to take into account is what is the height of water column. Okay, the second is the density of water. What is the density of water, which is represented by rho w. And the third one is the acceleration due to gravity. And by including all those factors, you can calculate the value of psi g, which equals psi g equals rho w, g and h. Okay, that means rho w is density of water, g is acceleration due to gravity. You know the value of acceleration due to gravity, and h is the height of the water column for which you are calculating the gravity potential. Okay, while dealing with water transport in the cell, I mean, while you are calculating the water potential at the cellular level, the gravitational potential or psi g, it is generally omitted as it is negligible. Okay, since the value of psi g is negligible in case of plant cells. Okay, when you are calculating the water potential at the cellular level, the value of psi g becomes negligible and hence it is omitted in the equations. And finally, the metric potential, which is represented by psi m, the surface to which water molecules are adsorbed, that surface is known as matrix. Okay, any surface that is able to adsorb the water molecules, adsorb means addition of water molecules to the surface. Okay, that surface is known as matrix. Okay, the metric potential is the component of water potential influenced by the presence of matrix. If you have matrix present in the system, the matrix will influence the water potential, because matrix is going to fix the water molecule. Say this is a matrix. Okay, this matrix will obviously attract the water molecules towards it, and when it attracts the water molecules towards it, their free energy will get reduced. Okay, so we can say that metric potential is negative as it binds water and decreases their free energy. जब ये water molecule है यहाँ पे, it gets associated with the surface of this matrix, its free energy will get reduced, and hence we can say matrix, the presence of matrix in a system reduces the water potential. Okay, it is appreciable in young cells due to presence of hydrophilic colloids. In case of tall plants, the value is negligible and usually omitted. Okay, metric potential, it is appreciable in young cells because young cells possess the hydrophilic colloids, but in case of tall plants, the value is negligible. Okay, the value is negligible and generally it is omitted. जो metric potential का value होता है in case of tall plants, because they do not possess that much hydrophilic colloids in their cells, the value of metric potential is omitted. And after omitting the gravity potential and metric potential, as their values are negligible at cellular level, the modified equation for water potential therefore becomes psi w equals psi s plus psi p. Okay, after omitting the values of gravity potential and metric potential because of their negligible values, the final equation for water potential becomes psi w equals psi s and psi p. Okay, if you are going to talk about this pure water has the highest possible water potential, which is 0. Okay, the highest possible water potential for any system is 0. जो pure water है, that is the water which is free of any solute, it is water potential is 0, and this is the highest known water potential. Okay, because for pure water in a beaker, the equation is as follows. If you are going to calculate the water potential for pure water, it will be like this: psi w equals psi s plus psi p. Okay, since we do not have any solute in the solvent, okay, its value will be 0. Here it will be 0. Okay, and there is no osmotic entry of water in the, say this is a cell. Okay, it is containing water without any solute. It is a container containing water without any solute. In this cell, the psi s is 0 because there is no solute present. Psi p is 0. It means there is no osmotic entry of water into the cell. Psi p will also be 0. Turgor pressure will be 0, or you can say hydrostatic pressure will be 0. So when psi w equals 0 plus 0, okay, obviously water potential will be 0. Okay, water potential, we can say water potential equals 0 for pure water. Okay, and when you are going to dissolve some solute in this, water potential will become negative. Okay, you have to remember this. Pure water always has 0 water potential, and the addition of solutes reduces the water potential to negative. So this is all about the different components of water potential. I hope you all understand this. See you soon with a new lesson. Till then, stay blessed and thank you.